All right, let's go and get started. TV and whatnot is loading up. So while it's loading up, I will get the sign-in sheet passed around. Um, Here is that. Okay, so a couple quick announcements. I told y'all I would have a homework for you all today, and I do. I have homework number 7. It is a homework on frames. Just a heads up, they're probably, and I mean it's a little tough to avoid, but I mean we don't have any exams until finals, so I think the trade-off is that we're probably going to have a rapid succession of homeworks between now and the end. Like that's the trade-off. So you know, it is what it is. I'm going to give you all an assignment today. I'm going to make it due Friday. Honestly, you could probably have it done Wednesday, but since there's a concrete exam on Wednesday, I've decided to not do that. Okay, so you won't have a homework and exam due on the same day. But in all honesty, you're probably going to have a homework that Friday, do the following Friday, and then another homework due the following Friday. You know, so that'll be sort of the trade-off. So, sound good? Okay. This homework is honestly it's pretty short. It honestly will be a little repetitive, but I think that's kind of the point. So on problem 1, I'm giving you a frame. 1, 2, 3, 4, 5, 6, 7, 8. There's that. Okay, so on problem 1, I'm giving you all a frame, and I'm giving you like, you know, a bunch of different members and a bunch of different boundary conditions. The idea is just to make sure that you all are comfortable with the use of the alignment chart. So the idea is, you know, you go through and just use the alignment chart to compute K. Now, I'm not giving you any loads for the column, so you couldn't compute tau even if you wanted to. So the idea is to just get comfortable with the alignment chart. Problem 2 is basically what we're going to dig into today, and maybe a little bit of Friday, but the idea behind problem 2 is to do a column design for a column in a frame, which is what that's really going to be the main topic of discussion today. Sound good? Okay, now that's due again the following Friday. Okay. All right, so as the sign-in sheet's going around, I'm going to go ahead and sort of get right into it, and we're going to discuss our last column topic, which is designing columns that are in frames. After that, the rest of the semester, we're in beam world. We are talking about beams. All right. Okay, so let's just recap on our last example. I know we trailed after a little bit, so you know, we went a little bit past 9:50, but I think it was kind of important. With all the makeup days and cancellations, I think we'll just let that one slide. It'll be all right. It'll be all right. Okay. We did this example, and one of the things I wanted you all to pick up is when we did this example, we did it 2 ways. One of them was considering elastic behavior, and one of them was considering inelastic behavior. Now, when we considered inelastic behavior, what happened to K? Like, we had a K value, and then we went and applied tau. What was the next K value? Was it higher or lower? Lower, okay? So if your K value goes down, what does that do to your capacity? Increases it. So since inelastic behavior is going to happen more often than not, especially in design world, I guess the baseline rule is when in doubt, use tau, okay? All it's going to do is help you out in the world of design, okay? Make sense? Okay, that's point 1. Now point 2, okay? When we calculated all these K values, we were calculating KX's. K's in the X direction. Give me one second. All right, K's in the X direction. For this frame, what is K in the Y direction going to be for all these columns? 1. Because all we're assuming is that it's a brace frame in this direction, but we don't know anything about the members. So the worst case scenario would be that K is 1. All right. Yes, sir. You're saying using tau would not be erring on the side of caution.
Yeah.
Okay, I see your point, and that's a good observation. However, here's the problem. Okay, the problem with not accounting for tau is that you're not accounting for the behavior that you know is going to happen. Let me put it like this. Okay, do you remember at the very beginning when we derived elastic buckling? And then I said, here's this really cool equation. We used the engineer's greatest differential equation solving tool. We used Wolfram Alpha, right, to solve the diffEq, right? And then we said, here's this equation. Oh, by the way, it's all wrong, right? And why was it wrong? What are the two reasons why it was wrong?
Residual stress.
And?
Geometric deformation.
There we go. Okay, all right. Now, residual stresses tend to affect a column's capacity more on the inelastic range. It tends to increase your likelihood for inelastic buckling. Sound good? Okay. Here's my point, okay? You do get a benefit from using tau, so I understand what you're saying, that erring on the side of caution would mean not using tau. However, by not using tau, we're also not recognizing reality. See, those alignment charts, just like the derivation of Euler buckling, assumed that the behavior was elastic. And I think we know by now that that's not the case. What I am saying is that this adjustment will not only help you, but it also adjusts your K values to better reflect reality. Okay? I guess another way of looking at it is if we ignored all this AISC spec and just used elastic buckling, in most cases we would be unconservative. Okay? So what I'm saying is that using tau really just brings our math closer to reality, and it has the added perk of upping our capacity a little bit. Now, let me also be clear. I'm not saying that it's going to up your capacity like 250%. That's not happening. I'm saying you're going to be able to squeak out an extra, 10 or 15 kips on some of these columns. So if all it took was a little bit of, we're talking about 958 kips or so. So if we're talking about squeaking out a couple more kips, no big deal. Okay? Does that make sense? All right, is everybody else okay with that? Again, we get an added perk from using tau, but really it's bringing our math a little closer to the side of reality. Sound good? Okay. Again, another point, Kx for all of these columns was computed using the alignment charts. Ky is 1. Sound good? Okay. All right, so let's talk about design. Okay, design for a column in a frame is absolutely no different than the design of a single column by itself. Let's see if you all remember how to do this, okay? We get our factored load, right? We say, all right, we got our factored load. Let's factor it. Let's take Fy as 50 KSI, and then we go into table 4.1 with our weak axis column, like KL in the weak axis. We pick out some trial shapes, and then we go back and check the strong axis, right? Remember that KX LX divided by RX over RY? Y'all remember that? Okay, here's the problem. KX takes a little more work than it did before. Before we just said, oh, it's 2, or oh, it's 1 point whatever. Here, we've got to do a little bit more work. So that's the only difference. But the point is, the procedure is exactly the same. Okay? So we've got this frame. Let's take a little bit of time and understand what's going on with this frame. Okay? So let's just sort of digest this before we do any math. And this, I'm not going to lie to you, this example is going to take a little while because we're going to have to go pretty methodical and do a fair amount of work. Okay, so let's design the indicated column and frame below. So we're designing that first story column, okay? So let's see. So first off, we know Fy is 50 KSI, which makes our life a little easier from using the design aids. We've got a dead load of 250 and a live load of 735, so that's good. Okay, now we're designing this column, okay? Let's take stock of a couple things. The bottom of our column is what? Fixed or pin? Pin. What does that mean from an analysis standpoint? What does that do? See if you all remember. G is 10, right? So G is going to be 10 on the bottom. Now G on the top, we're going to need to compute the G value at the top of the column, right? Now, in order to calculate G, we need the stiffness of all the columns and the stiffness of all the girders. Now, the girders we know. We've got W21 by 83s that are, what, 45 feet long? Okay, so we know that. Now, for the columns, this would be tricky without this statement. Okay, so we're designing this column, but whatever column we pick, we assume that this column is the same as the one below. So if we pick a W14 by 90 here, we'll assume this is a W14 by 90 as well, which is not an off-the-wall assumption. It is very common in the erection of steel structures that you erect columns in sort of two-story increments. So, you know, that first-story column and that second-story column are actually the same shape. You know, on this story, the design's probably a little conservative because you think the taller you get, the forces on those columns tends to decrease a little bit. But from a constructability standpoint, it makes sense that this column and this column actually physically be the same piece. So you would erect and then go from there. Then erect another 2 stories and go, and that's how you build your frame. Okay. Does that make sense? Everybody okay with that? So that's not an uncommon assumption. Okay. All right, a couple other things. All right, so this is the x-axis, everything that you see over here. And you can tell not only by the label, but the images showing the orientation of your columns and your beams. If we're talking about flexure in this way, we're talking about the columns flexing about their strong axis. Sound good? Now, all we know about the weak axis is that it's a braced frame, right? So if it's a braced frame, what do we know about K in the y direction? 1, right? It could be anywhere between 0.5 and 1, but we don't know any of these members going into it. So, you know, first off, a starting value for design, K values equal to 1 would make sense. But even if you don't want to iterate down the line, K equals 1 would be a conservative approach. Sound good? All right, does anybody have any questions before we get started on this? Again, this example is going to take a little while. So, sound good? Okay. All right. So, let's start off. Well, you tell me, where should we start off? Of course, there we go. This stuff's becoming second nature at this point, isn't it? I have in some instances. I just don't want to make, I want to make sure you don't forget, you know. Can't forget this stuff. I mean, there's certain things in a civil engineering degree program you'll never forget when you get out of here. What's the unit weight of water? There, see. Depends on if it's SI or US use, but you didn't forget, right? Didn't forget that. What's that? Oh, I don't use unit weight of water, and I still remember it. What's that? All right, factored load. All right. PU equals 1.2 P dead plus 1.6 P live equals 1.2 times what? Times what? Is 735? And what do we get? Okay. All right. Now to go into table 4.1, we need y-axis properties. So for a given column, so we'll say for the y-axis, we're going to say ky is 1, and we're going to say ly is, how long is each of those column segments? 14 feet. So KL in the y direction is 14 feet. That's not so bad, right? Okay. All right. Now here's what we're going to do. All right. We're going to go into the manual. We're going to go to table 4.1. And you remember how this works, right? We start at the W14s and we find the lightest shape that we can find. Okay? We're going to do things a little differently. I wanted you all to get some experience with the manual before I show you what I am about to show you, okay? It's just something that you want to keep your eye out for when you're selecting shapes. So let's go to Table 4.1. Let's go to Table 4.1, and let's start picking some column shapes. So let's start with W14s. What is the lightest W14 shape that you can find? Remember, it's off a effective length of 14 feet and a capacity of 1476. Okay, I got a 14 by 132. Do you have a second on that? You got that? Okay, so well, it's not a W14 by 800, right? It'll work though, right? It's the W12 by 800. I think that's what it is. All right. Now, what was our VPN for that? Just go ahead and write it down. The capacity. And okay, we're going to need a couple other things while we're at it, okay? We're going to need Rx over Ry. So that's all right there, 1.67. And another thing that you'll notice if you look down at the bottom, that the moment of inertia and the areas are there. Now, which moment of inertia do we need? Do we need Ix or do we need Iy? Think, what are we going to use it for? What are we going to use the moment of inertia for? No, think about it. What are we going to use Ix for? To calculate the G values, right? We're going to calculate K in the X direction. So we need the moments of inertia about the X direction in order to calculate G. So what is the moment of inertia? Should be down there on the bottom. There we go. Okay. Now one more, we're going to need the area. What's the area? Bless you. Okay. Now, okay. Let's see. Everybody from, bless you. Everybody from, we'll say Kyle this way. Tell me the next W12 that'll work. Everybody from Kyle this way. Find me the next, or the first W12 that will work. This is something I haven't shown you all before because I wanted you all to get some experience with Table 4.1, and then you could see this stuff a little easier. W12 by 152. So are you all in agreement that the W12 by 152 is the lightest W12? Okay, W12 by 152. Keep that in your head. Now, everybody over here, what is the next W14? What's the next one? We have a W12 by 130, or W14 by 132. What's the next W14? 145. Okay, so here's what I'm proposing. You all want to find the lightest shape, right? I propose that we go ahead and add the next one as the W14 by 145. Because what you all are saying over here is that the lightest W12 is the W12 by 152. And I'm saying if we can get this one to work, well, I'm going to pick this one over that one because it's lighter, all right? Does that make sense?
What if it doesn't fit in the architectures? Sure it will.
No, what?
I said, I'm sure it will,
What, you sure that'll work?
eventually. Yeah. I mean, it's heavier than the latest W14 section we defined.
But maybe the lightest W14 section doesn't work. Just bear with me. Just bear with me. What's that? Oh, I love this job. All right, so everybody over here on the left side of the room, W14 is about 145, so help me out. What's VPN? 1690. What's the RX over RY? Somebody else. 1.59. The moment of inertia, somebody else. 1710. And the gross area, somebody else. 42.7. All right, so over here, okay, VPN, what do we got? RX over RY. Okay, somebody else, IX. Gross area, somebody else. Okay. Now here's another added perk to how this problem is laid out. Okay, these are these final designs or are they trial shapes? They're trials because these are all selected based off the weak axis. We need to select based off the strong axis. Or we need to verify based on the strong axis. One nice thing about how these are arranged, they're arranged in terms of economy. Like section 1's the lightest, section 2, and then section 3 out of these 3 is the heaviest, right? What that means is once we check a strong axis section and find that it works, what do? We stop. We're done, right? Well, we stop for our design. We should still go back and check that capacity using section E3 or table 422 or something like that. But you are correct that we stop with our design. In other words, once we find a section that works, we're done, okay? Sound good? Now, while we're at it, I actually don't remember. Were there any W8s or W10s that would even work? I could almost guess, I mean, that's 1.476 million pounds. I don't think there's any W8s that are going to work. What about W10s? No. So it's either W14s or W12s anyways. So let's say none of these worked. What would you do? No, I mean, we've said the W14 by 730 will work. No, my point is, what's the next one? For the W12s? For the W14. So you see what I mean? You would just keep going until you find one that works. And again, I promise, the W14 by 730, it'll work. All right, so does that make sense? Okay, so let's just sort of get into it. Now, how do we verify the strong axis capacity? We take KXLX and we divide it by RX over RY, right? What's KX? We don't know, right? So we have to go through and do some math. So let's do section 1, all right? Do better now. W14 by 132. Okay. So let's start off with GA, okay? So it's the sum of the I over L for the columns divided by the sum of the I over L for the girders. So I guess for this, this whole problem, what's one I value that we forgot to look up? The W21 by 83, the beams, right? So we might as well look that up on the side. What is the IX for a W21 by 83? So maybe I'll put this up here. So what is IX for a W21 by 83? Got to go back to the front of the manual, right? Now, does everybody understand why I'm looking that value up? Those are the beams on that frame. 1830. Yes. If you want to use B for beams, you can. It's just as long as you're calculating it right. I don't know that it really matters. But yeah, girders. So. All right. So let's take a look at this math. So first off, how many columns are framing into that joint on joint A? Let me pull the frame up. If we're talking about joint A, yeah, that's probably a good question. Yeah. Joint A, we'll say joint A is the top, joint B is the bottom. So how many columns are framing into this joint right here? 2. We got a column here and a column here, right? What can you tell me about those 2 columns? They're the same, right? So I'm going to have an I over L for this column and an I over L for this column. And I over L plus I over L is just 2I over L, right? So yes, because they're 2 individual bracing segments. That's a very good point. And yes, because they're 2 unbraced lengths, we're treating them as two different segments. That's a good point. All right. So I'm going to say this is 2 times, now we're dealing with the 14 by 132, so is that 1530 inches to the 4th divided by, how long is the column? 14 feet. And then now how many girders are framing into that joint? 2, right? Are they the same? What's that? See? Is that something we said? All right. So let's see. So what's the moment of inertia? 1830 divided by, now how long are they? Do we need to worry about units? Do we really need to worry about 2's? They cancel out. So I just want you to recognize that the 2's are there. So when you go back and you're saying, why was there a 2 there? Oh, that's why there was a 2 there. So what do we get? .69, you said? Which one did you say? 6.9. Do I have a second on that? All right. Now, is that assuming elastic behavior or inelastic behavior? Should we go ahead and deal with inelastic behavior right now? Let's go ahead and do it. All right. So how do we do that? Oh, I'll help you out. I'll start you out. Okay? All right. So first thing that we need is, and I heard somebody say it, PU over FYAG. So what's PU for this column? Make sure everybody's paying attention. Divided by 50 KSI times what? See, now you're seeing why the area came into play, right? See? What are the units on this calculation going to be? Unitless, there we go. So what do we get? 0.761. Do I have a second on that? All right. It's 0.761. Now, what does that mean for tau? What is tau? It's that long equation that ultimately really isn't so long because it's 4, or here, let me put tau there. Tau is 4 PU over FYAG times 1 minus PU over FYAG, which is just 4 times this fraction, which is 0.761 times 1 minus 0.761. What do we got? 0.728, did you say? Do I have a second on that? Okay. So, therefore, we'll adjust our bottom value, or our G value with tau, so 0.728 times 2.69. And what does that yield? Excuse me. And we'll just go to 2 decimal places because remember what we're going to use this for. We're going to throw it in the alignment chart. 1.96. Do I have a second on that? Okay. Now, would you agree that that is what we need to go into the alignment chart with for the top joint? Okay. Now, let's carry out this discussion. For the bottom joint, what is the elastic G value? 10. What is the inelastic G value? 10, right? You don't adjust it, right? So on the bottom, we just go in with G sub B of 10 because it's pinned.
So the unadjusted ones are elastic?
Say what?
Without tau, it's elastic?
Yes, exactly right. Because tau, the name for tau is the inelastic stiffness reduction factor. Like, that's what it's for. So with these, tell me what is Kx? About what is Kx? So you all obviously, everybody has a straight edge, right? Oh, now. There we go.
He's real sleepy. You ever been real sleepy before?
I have been sleepy before. Oh, I love this job. So what do we got for K values? Anybody got something? 2.1? See, I got a little bit high. I got 2.15.
Yeah, well, 2.14.
Now, here's the thing. Make sure that you're lining up with the right marks, okay? So, you know, for instance, if you're on the 2 side, the distance between each one of those marks is 0.2 between 2 and 3, okay? So, like, here, like 2, then tick, 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 3. So that's 2.2, 2.4, 2.6, 2.8. Who's not seeing it? Is everybody else? It's okay if you're not. Yeah, no. Well, let's see. So,
Pretty close.
all right. So yeah, I recognize it's a little tough to see. So, you know, what do we have? So we got 6, 7, 8, 9. So maybe about like right there. Like right there. So that's 10. Then probably something about like that, honestly. So.
That looks like.
Yeah, that does. Yeah. Tell you what. I will negotiate you with you all a little bit. We'll say it's 2.1, what, 3, 2, 2? I heard enough 3s. I'm just going to go with 3. So.
That's kind of what I was thinking.
No. That's just opinions. Again, when we grade this assignment, I know that there's going to be differences. Like some of you are going to say 2.12. Some of you might even say 2.09. If you say 3.78, That's off. Okay, and that's fine, you know, I understand. Now, the way that I got the 2.15 is I goal seek the equation, so. Okay, now. What's that? So, yeah. Yeah. That's why I'm using it as my baseline. Like, that's how when I grade, I use that as the baseline. And if you're within, like, a tenth or so, I'm going to be fine. But if you're getting, like, 6 points, I was like, okay, you're off. So. Sound good? Okay, does everybody have all this? All right, let me ask you a question then. If you have Kx, what is KLX going to be? And what is the length? So what is that? Say it again. 29.82 feet. Let's see if you all remember where to use that. Okay. All right. We take KL effective, and we say that that's KL, whoop, the pen's getting away from me, KL in the x direction divided by Rx over Ry. So that's 29.82 feet divided by, what's Rx over Ry for this column? And what do we get? All right, so we would need to do some interpolation between, what, 17 and 18? Is that what you're saying? So what's the word? What's that? Why do you say that? Oh, hold on. Oh, wait. Think about it. Think about that. Longer length means longer slenderness. Larger slenderness means weaker column. If it was the other way around, if it was like 12, then we could have that. Oh. That's easy. That's easy to mix up. There's nothing wrong with that. Okay. So, what's the word? It's too weak. Why is it too weak? What's the value for 17 and for 18? All right, so 1410 and 1370. So the answer is somewhere between 1410 and 1370. Is that good enough? No, because the load is what, 1476, right? So is the W14 by 132 good? It's trash. Kick that column to the curb, right? So W14 by 132 is no good. What's that? All right, hold on, let me write this. I'll show you. And I'm writing that so that everybody sees that. Okay, so I'm on page 4-15. Yeah. And if you go to page 4-15, go to the W14 by 132 and look at what the capacities are for 17 and 18 feet. Okay, what are they? No, what are the numbers? Yeah, see, look, do you see where I'm getting? Do you see? Yeah. This is our effective length, so to interpolate it would have to be between 1410 and 1370. Regardless of what the value is, it's less than PU. PU is 1476. So that's why I'm saying this column is no good. All right. Does this make sense? I really want this part to make sense. So if you've got any questions, please, now is the time. So, unfortunately, We got to keep on trucking. Oh. But once you've done it, we literally are going to do the exact same steps again for column number 2. Does everybody have all this? Then we'll go to number 3. Now, you know me, so on exams, we'll have to get to like column number 7 before we get one that works. All right, so column number 2, W14 by 145. What's first step? G. So the calculation is exactly the same, except we have a different column. The sum of I over L for the columns divided by the sum of I over L for the girders. So there's 2 columns, right? Framing into each joint. Now what's the moment of inertia of that column? 1710. Divided by what? What was the, same thing. No, I couldn't remember the length. I was getting y'all to tell me the length. This is 2, you said 1830? 45. So what do we get here? 3.004. You better hope you get something different, otherwise we're going to be doing this over and over again. You do the same thing to get a different response, right? If we were, otherwise it would. Well, we're not technically doing the same thing because we're plugging in different values. If we, all right. Next one's PU over FYAG. So 1476 times 50 KSI. Say it again. What do we get?
What did you say we do if it's not 50 KSI?
If you don't get 50 KSI, then you're going, well, I'll just go ahead and tell you, column design becomes much more complicated. You'd basically need a new table for one, essentially. Pretty much, yeah. Now, AISC actually publishes them online for like 65 KSI steels. They use that for really large-scale buildings. So what do we get here? 691? All right. What does that mean? What's our tau? I'll just say 4 times 0.691 times 1 minus 0.691. And what do we get? Say it again. So therefore, tau GA equals what? What do we get? If I have a second on that? All right. Well, it's a different column, though. It's a heavier column. Okay, so that's for the top of the column. What's for the bottom? So Now the debate begins, right? What's that? The great debate. What'd you get? 2.21. I just make it 2.22 just to be. I'm just being difficult. Is everybody else okay with that? While we're on the topic of the alignment charts, would you like me to print off about 50 copies and just leave them outside my office for all the lines that are being drawn on these? No, I'm being serious. Like, would having extra copies help? It's on Blackboard. That's what the straight edges were for. Okay, now, we've got KX. We can compute KL effective, and what do we get? So we get KX LX divided by RX over RY, and what is that? So it's 2.21 times what? How long is the column? Divided by what's Rx over Ry for this column? Say it again. Okay, so what do we get right here? So what do we get for this? Second on that? What do we do with that? So what do we interpolate between? 19 and 20. So what are the values for 19 and 20?
15, 10, and 14, 6.
Is it worth doing the interpolation? Yes, it is. So phi PN at KL equals 19 feet is 1510, and phi PN at KL is 20 feet is 1470.
I don't think it's worth doing it.
Why?
Because it's only 6 hips. It's 56 and it's closer to the 19, so it's higher.
But okay, let's say it was 19.5.
I still wouldn't think it'd be worth it. If it was 19.5.
Okay, hold.
On a homework, I probably wouldn't do it.
On a test, that's not happening. Like I say, engineering judgment. We're good. There we go.
It'd be different if it was 19.96. Then I might say it's not worth it, because 19.96 would be so close to the 1470 that it probably isn't going to work. But this is basically 19 and a half. Now, 19 and a half, halfway in between, that'd be like 1490. So that's higher than 1476. If you go through and do the interpolation, you'll get 1491.6. Is this column, what was it, garbage as the front? This is a good column, right? So it is not rubbish. Use a W14 by 145. That's it. That example was quicker than I thought. I thought it was going to go into tomorrow or Friday.
The other one check.
make sure you check the capacity of that column using E3. Yeah. That's holding up over 1 million pounds. It's worth a little bit of math.
You can tell by looking at it, though.
What if you made a mathematical mistake?
That's not the interesting thing.
In the eyes of my brother.
All right. Any questions? That's columns. Rest of the semester. Beams. All right. That's all I got. We'll see y'all next time or in a couple minutes.